So, welcome to the second lecture in the two-part lecture series on networks and distributed systems. So, here we will mostly look at distributed file systems. So, we'll look at small-scale distributed file systems for a lab or for a corporate setup, and then very large-scale distributed systems for, let's say, web scale, like for Google, Amazon, Facebook, and so on. So for small scale distributed file systems, the most popular examples are NFS, Network File System, and AFS. So AFS has an open version known as Open AFS. AFS stands for Andrew File System. So pretty much both of them have similar design principles, even though they are slightly different. I'll talk about that. So what happens is that they have a set of servers, so typically a single server, which stores the files as well as the metadata on either local storage or attached storage. The address of the server is known. So, what all the clients do is that they connect to the server and say that, look, I need a certain file. The server is responsible for authentication, for checking whether the client genuinely deserves the file or not, for checking file permissions, and finally delivering the file to the client. So, the changes that the client makes are then propagated to the file, propagated to the version of the file that is stored with the server. So, of course, multiple client machines can access the same file. So, in this case, conflicts are resolved in file system specific manner. So, typically, the Unix conflict resolution system is used, which means that the last writer wins. But the key point is that NFS typically caches or stores locally chunks of files, whereas AFS stores the entire file. So AFS in a certain sense is more efficient because the entire file is stored, and in a certain sense is less efficient because if the file is very large, then NFS tends to perform better because it does not cache the full file. There is still a single point of failure because if the server crashes, the file is pretty much gone. And the server is also a bottleneck for data and metadata requests. So this does indeed pose problems with both scalability as well as bandwidth. So this is a model of the DFS system where we have multiple clients connected to a network. And then there is a server that is also connected to the network, and it's a single server, as you can see. So the moment we have a single server, we have a centralized point of failure. So let's look at ways where we don't have this centralized single point of failure. So we can have a cluster-based distributed file system model, which is by design much more fault tolerant, much more scalable. So examples include the Google file system, which is of course large web scale for petabytes of data. The Hadoop distributed file system, which is again for large scale data oriented computing. So in this case, there is of course one master metadata server, but need not be. There could be several master metadata servers as well. And there is no centralization in the sense we have several data servers that hold chunks or portions of files. And there is a fair amount of redundancy in the system in the sense if one data server goes down, others can take over. So the metadata server keeps mapping of which data servers hold which chunks. But then again, modern avatars of this don't actually require a metadata server. And there is a method called a distributed hash table via which you don't need a single server for this mapping for functionality. So they map, so they keep a lot of data. So they store the file data and also the directory data, which is a hierarchical mapping. But a directory can also be stored as a single file, as we have been seeing up till now. And because there is replication, there is no single point of failure. If one data server goes down, well, so be it. So here is the idea. We have multiple clients. As I have said, this is a slightly outdated diagram. Modern versions have several metadata servers. And definitely we have a lot of data servers with chunks of files with them. So the Google file system, it was designed with the following observations: that hardware component failures are the norm, in the sense hardware does fail, machines fail, networks fail, everything fails. The file stored particularly on a web scale system where we're looking at a large amount of data, right, can be very high. So we are entering the age of big data, super big data. So it can be very, very large. And furthermore, when we are looking at large data stores, which can be anything starting from Facebook photos to anything, so we seldom delete, let's say, our tweets or Facebook photos. We mostly append. So we mostly append to overwriting data. We seldom delete. That is why these file systems are not tailored towards deletion. They are more like for appending. Then we redesign applications and file system. The API, it increases the system flexibility. So this basically means that we want to create a really flexible system, and for that, the entire API of the file system was redesigned so that applications can use this. So the two most common calls are essentially put and get. So put means that you put some data into the file system, get means you retrieve it. And so the file system was made far simpler because this is how it is going to scale. This is how it is going to become robust. And they became a part of the new API, which if you would compare with the ext4 will not provide that many features. In fact, it will be very rudimentary. But the good thing will be that it will scale and will be extremely fault tolerant. So then this is a modularized software layer. And then of course we can run the MapReduce system, which is a very large distributed computing system, which can sit on top of GFS and carry out large scale parallel computations, and can also sit on top of the Hadoop file system stack. And this is how many corporate systems, enterprise systems, web scale systems actually manage and process their data. So let's now look at some of the common underlying concepts over here. So there are two important concepts, naming and transparency. So naming is the mapping between logical and physical objects, which is a very key idea in operating systems, in the sense that virtual memory, there's a naming aspect. We have looked at the naming aspect in virtual machines, for example. The other is multi-level mapping. So the moment we have a file, we're essentially abstracting out the disk. So we are not seeing, we want to hide the detail of how and where this data actually sits on the disk. Because we are abstracting that out, we are having a file. And as far as the programmer or the rest of the system is concerned, we just access the file byte by byte. That's all that we do. So we don't do anything more than that. And this abstracts out the file. This abstracts the physical device. It abstracts the disk. This is something that we would like to do in a distributed file system also. So a transparent distributed file system like the ones that I just talked about, they hide the physical location of the network files. Every network file is essentially identified by its name. It is also replicated across several sites, but we never get to see that. And there is, needless to say, a mapping. So typically what happens is internally, the mapping would return a set of sites that contain the replicas of the file. But the point is all of this is hidden from the user. So this is all done by the internal file system layer, where it connects to the data servers, it connects to the metadata servers, retrieves the replicas. Often, even for the same file chunk, there may be multiple replicas which may be out of sync. Mainly because the same file could be accessed in multiple places or something went down. So there are methods of reconciling the different versions of a file. But what the user basically sees is a single file, regardless of where it is stored and regardless of how it is stored. So this is the key idea of naming and transparency, which is to virtualize the file application, file access process. So regarding naming, these are two very common terms which are used in distributed systems. They are known as location transparency and location independence. Location transparency means that the file name as such does not reveal the file's physical storage location. We have talked about that. And the other is location independence, which means that if this physical storage location changes, the name of the file doesn't have to be changed, right? But if you actually look at it in a traditional Unix system, if a file moves from, let's say, my machine to somebody else's machine, the same name or the same path will not work. The path has to change. But in a distributed file system, thankfully, this is not there. So, regardless of the location, the name remains the same. So, most such file systems use a static location transparent mapping for user level names. In the sense, they create a virtual file system over a large number of physical machines, where if this is the path of a file, that's the path of a file, regardless of where it is stored. So the internal software layer's job is to locate the physical file from the path. There is no support for file migration in the sense among the sites. We don't get to see that. Of course, as I have said, as I have argued earlier, there is a need for a different API. In the sense, we need to slightly relax the strict Unix semantics that the entire file is visible in one go, the last writer wins, and so on, because then it will become fairly hard to implement these distributed systems. So sometimes the POSIX standards, which Unix also follows, they are not followed. And of course, this the client doesn't get to see, but from the behavior of the file system, the client will ultimately get to know. But this consistency requirement is slightly relaxed. What Amazon S3 does, which is also a distributed file system, is that it provides blocks of storage using an API based system, which are internally stored dynamically across a set of sites, and data is moved as is considered necessary. So there are different naming schemes in distributed file systems. So what we have traditionally is that files are named as a combination of their host name and local name. So basically you can say that this is, let's say, the host name, and then there will be a local path slash something slash something slash something. This is no doubt a unique system-wide name, but neither is it location transparent nor is it location independent. So this does not satisfy our requirements. The other is that we follow an NFS kind of mounting kind of approach where we have a local file system. We take a remote file system and we mount it on our system. So in this case, we are attaching remote directories to local directories. So we are giving the appearance of a coherent structure, and basically there is a path system. So previously mounted remote directories can be accessed transparently, but this again is not all that uh, well, it's location transparent, no doubt, in the sense that we don't actually get to see it. But the first time you mount it is not location transparent, because for mounting we'll have to provide the host name and a local name. And it's not location independent because once it is mounted, we move the physical location, then of course the mount point will change. So what we actually need is that we need a file system which is not like NFS and AFS, but it is more like the Google and Hadoop file systems that we have seen, where the naming spans all the file systems of this in the entire system. It is one single virtual directory. If a given server is down or it is unavailable, then what will happen is that the internal system will take care, because there is a fair amount of redundancy. Even if it cannot take care, then maybe some directories will become unavailable, but a large part of the file system will still be available. So this is, in a true sense, location transparent and location independent. So let me go back to the definition once again. Location transparency means that the name of the file does not reveal its physical location. If, let's say, we have the host name in the name of the file, it doesn't remain location transparent. Location independence means that the name of the file doesn't change when the physical location of the file changes. So this again is not possible in systems where you have to physically go and mount based on the host name. So we need a We need a layer which truly virtualizes. So this is where these web scale file systems come in really handy. So Amazon's file systems that are used in AWS like S3 and so on all fall in that class. So for remote file access, so consider a user who's requesting access to a remote file. The server has to do several things. The server has to authenticate the user in the sense if there is a client machine, it is requesting for a file from the server. The server has to verify the credentials, and after that, an actual data transfer will take place. So, the remote service mechanism is one such transfer approach where you send a stream of requests for accesses. The server does that and it forwards it. And we have already seen the remote procedure call as one of the ways of doing so. So, what we have discussed is that the moment we have a client server kind of setup, what really happens is like this, that we have a client and we have a server. So, then the client will store a part of the file. Another client will store a part of the file if it's accessing the same file at the same time, or roughly at the same time, in the sense it accessed and then it stopped accessing, but it still has it. So what can happen is that there will be conflicting updates. So they may not be the same file block, but different blocks of the file. So there is a need to actually ensure that whatever is cached among the clients, it is kept consistent. So there's a cache consistency problem. So typically, if you would go with Unix like semantics, where the last writer wins, and so here the idea is that the moment a file is closed, so the moment you close a file, then you don't keep any dirty blocks in the cache. What you basically do is that they are all committed back to the server. And of course, the one to commit at the end is the one whose version ultimately persists. So this is of course one of the semantics, but there are many different kinds of semantics of cache consistency in file system. So this is beyond the scope of this course, but I just want to let you know that this is a very hot area of research and this is still alive, right? As of 2022, it's still alive. So this is essentially a form of a network virtual memory, albeit at the level of files. And depending upon what kind of correctness requirement we want, different file consistency, file cache consistency models are possible. So let us now look at the cache location issue of disk versus main memory. So the question is, where do we keep these file caches, right? So we can keep them on the disk. They are more reliable. And let's say the machine goes down and then it comes up. It can get the cache data from the disk, right? It'll still be there during recovery. And also because of RAID and other technologies, disks have a built-in reliability. We can also have a cache on in main memory. It has some disadvantages, several advantages. Let's start with the sunny side, the positive side first. It permits workstations to be diskless in the sense you can just not have a hard disk. It will reduce the cost and also the form factor. So it'll just have a main memory where you'll have cache blocks in the sense that the client will just have main memory and then it will get part of the boot sector while it is booting from a server and just boot. Data is accessed far more quickly with high performances. Server caches that are used to speed up disk IO are all there in main memory. And also the other thing is that we can have a very fast consistency mechanism across the main memories of all the clients. The problem is that if let's say for some reason there is a power off, a power shutdown, given the fact that the main memory is volatile, we will tend to lose all the data. So this is where the performance advantages will go away. But let me also share a little bit of history. So one of the advantages of the Google system is that it primarily relied on having lots and lots and lots of cheap main memory, where the search data, the search results were all kept in memory. So this is what gave Google its tremendous speed. This is not something that was done earlier, so they did involve disk accesses, which made the entire search process very slow. And disks also don't have the kind of bandwidth that main memory has. So this has been there since the era of Google, which means, let's say, from the late 90s. But of course, having things in main memory does make things fast as long as we can manage the issue of data consistency and correctness. So there, of course, can be many cache update policies in this case. It's not the regular CPU cache; it's the file cache. Just to remind. So we can have a write through policy where as soon as we write something to the cache, if it's a main memory cache, we send it to the disk, or let's say if it's a client cache, we send it to the server. So this is a write through policy which makes the entire system quite reliable, but needless to say, performance is poor. So it's not a bad idea. What is much more common is delayed write or write back scheme, where modifications are written to the server later. So this ensures that write access is complete very quickly. And furthermore, before the final write back, if the same data is written over and over and over again, only the last write is sent. So this does reduce the bandwidth requirement. Reliability and consistency are an issue because you can have many of these semi-written caches and the server will always have a version which is quite outdated. There is also the possibility that if a client crashes, right? So if there's a client crashing, right? We may lose valuable data and we also may have the problem of inconsistency where some of the new data has been sent to the server and the old data is still and sorry, some new data has been sent to the server but other new data has not been sent. So one approach could be that we scan the cache at regular intervals and flush the blocks, which means write to the server blocks that have been modified since the last scan. The other is the Unix like approach, which I was mentioning a few slides earlier, which is write on close, which basically means we write data back to the server when the file is closed. So that is when we do a bulk write. So this is what a traditional file system would do that follows Unix semantics. This is also best for files that are open for very long periods, seldom shared, yet frequently modified. So for that, we would do that. But let's see if there is something which is uh, shared a lot, this may not be the right idea. So particularly if there is a single writer and many readers and the readers want to get the updates as soon as possible, this is not really the best idea. Now let's come to consistency. How do we ensure that a locally cached copy is consistent with the master copy? So there are two approaches, approach one and approach two. Approach one is a client initiated approach where the client that is trying to get a copy of the file initiates a validity check at the server because it may have previously cached blocks of the file. So one thing that can be done is you take a block of the file, you compute a MD5 hash and just send the hash to the server. The server will verify the hash. If the hash matches, the blocks are the same. The server checks whether the local data is consistent with the master copy. Then we can have a server initiated approach where the server will record for each client the parts of the file that it caches. So this is where the server needs to maintain state. So I need to mention over here that protocols like NFS and so on are stateless. So in this case, the server does not maintain any state about the clients. But we have other protocols like AFS and so on, where the server does maintain state. So in this case, this is an example of the server actually maintaining state. So when the server detects such kind of a potential inconsistency, it needs to react. So in cluster-based distributed file systems of this kind, cache consistency, the issue of cache consistency is way more complicated And there is a need to slightly relax it, otherwise, we'll not get good performance. So, looking at HDFS, it allows append only write operations in the sense it doesn't allow random writes and modifications. And furthermore, it assumes that there is a single file writer which writes and the rest read. So, these are the unique limitations that it puts. The other is a Google file system, which does allow random writes with concurrent writers. So this complicates the write consistency requirements guarantees for GFS as opposed to HDFS, which is way simpler. So of course, if we want to provide a more stronger consistency model and more features, for example, random writes with concurrent writers, then of course performance takes a hit or complexity takes a hit. So this ends chapter 19, which was a very quick and brief short introduction to networks and distributed systems.